Or they look like that. Still go through 0, 1. Let's see, let me put that in a place where I can do all my writing. Still go through 0, 1, and they still go through 1 comma the base. It's still f of x equals a to the x, but now you have a positive value smaller than 1. If you think about what happens for base a equal 1, it's kind of boring. I'll leave that to you. But basically, exponential graphs have one of those two shapes. And then if you're trying to sketch something like g of x equals 1/2 to the x minus 4, it looks like an awful function, but it's going to be shaped an awful lot like this one, except substitute x minus 4 for x, shift the whole thing 4 units in the positive x direction. So you have some graphs that you can graph from these using transformations. Actually not terribly difficult. Okay, let me just put up a couple more examples so you're ready for the homework. And we'll be good to go. Let's see. Oh yeah. You might recall that way back when we looked at linear functions for the first time, you had some homework problems where you had to look at a table of inputs and outputs and identify a linear function. That red stuff is really hard to erase. Let's see. How about inputs -1, 0, 1, 2, and outputs -7, -4, -1, and 2. And then let's also look at another input-output relationship. Call this one G. With the same inputs and outputs of 1/3, 1, 3, 9. Okay, so back when, I hope you'll recall, you looked at a data table with changes in x that were consistent in the inputs. So this is add 1, add 1, add 1. Delta x is 1 in every case. And then you look over here at the delta y's and you notice that, let's see, I think you positive 3. If you add 3, you get to the next one. And we kind of observed that equal changes in x going along with equal changes in y, well, since delta x, pardon me, rise over run, delta y over delta x is a constant, a slope for a line, this would be characteristic of linear. So equal changes in x, equal changes, addition or subtraction in y. Okay, now let's take a look down here at what's going on. Again, I've got equal changes in x. I'm adding 1 every time. But over here, if I want to see the pattern, 1/3 to 1 to 3 to 9, they're not equal additions that are happening or subtractions, but multiplications. I think if you multiply times 3, you get to the next output. And as long as the inputs are equally spaced and the outputs have equal ratios, not differences, but you're having to multiply by the same number to get there, even if it was fractional, multiply by the same thing to get to the next input. That's characteristic of exponential. Okay, so you'll see some problems like that where you look at tables and just see whether they're linear or exponential or neither. One other type of problem, and that is a type of equation. You'll see some exponential equations where maybe you're asked to solve 4 to the x minus 1 equals 8 to the x. So you're looking to solve an equation with x in the exponent. That's an exponential equation. We'll look at other techniques for these in another couple of weeks, but for now, the method we'll have for solving some of these is called the common base method. Common base method. And basically what you do is write everything with one exponential base, one base. In this case, 4 and 8 can both be written as powers of 2. So rewrite this as 2 squared, or is the second power of 2, raised to the x minus 1. And since 8 is 2 cubed, the third power of 2, you could rewrite that equation like so. And then you might recall from the memory jogger, you had some expressions like this, exponential expressions, and a property of exponents is that when you have a power raised to a power, exponential expression with an exponent applied to it, that's a situation where you multiply exponents. So I'm going to distribute that, 2 raised to the 2x minus 2, and over here I'm going to multiply 3 times x. So you get this situation where you've got two different sides of the equation with the same exponent, or the same base rather, and different exponents. And it won't surprise you that this means the exponents have to be equal. Actually, that's a property of the fact that exponential functions are 1 to 1. But this will be pretty natural for you that if 2 raised to the 2x minus 2 is equal to 2 raised to the 3x, then 2x minus 2 has to be equal to 3x. And let me solve that equation by subtracting 2x from both sides, and that's it. I get x equal negative 2. I think if I were to check that, if I can smash this into the margin, don't know if I can or not, put negative 2 in for x, I think you get 4 to the negative 3 equals 8 to the negative 2, and that's 1 over 4 cubed, 1 over 4 times 4 times 4, equals 1 over 8 squared. Yeah. So those are checkable like any other equation. What have I left off? One thing. You will see in the homework here some use of the natural exponential base e. So you know, for instance, that pi is a transcendental irrational. It's about 3.14. Okay, now you're going to see e, which is a transcendental irrational, the natural exponential base, which is about 2.7. For just ballparking e, think it's around 2.7. But it's a transcendental irrational. It doesn't have a decimal expansion that terminates anywhere. It's about 2.7182818459045. It continues. I don't know why. That one's easier to remember than pi. It's got some kind of patterning in it. But obviously, that's not going to be useful to write out that many digits most of the time. Think of it as approximately 2.7. And note that some of the problems are just going to ask you to find a power of e, so that if you're finding e to the 1.7 power, just note that on your calculator, the second function of the ln, it's actually natural logarithm. It says ln, and it's like kind of lower left on the calculator. The second function of that is an e to the x. So second, e to the x, 1.7, enter. Have fun.